Hello, my name is Anshu Singh, and I will be presenting our work, Human Attributes Prediction from Privacy Preserving Conditions. Facial analytics has many applications helping people in general. However, the unconsented collection and use of visual data with faces can lead to privacy breaches and attacks. Now, the main problem is how to balance the trade-off between privacy and utility for visual analytics with faces. Before I move on to our approach towards solving this problem, let me introduce some of the terminologies that I will be using in the rest of the talk. Situational context is everything except for a target. Context is everything except for a target's head. Now, our take on the privacy utility trade-off includes we study the commonly used human attributes, that is emotion, age, and gender from image data. We use the blocking obfuscation technique on the faces for preventing identification. Moreover, we consider different privacy scenarios by increasing the amount of blocking in the face region of a target. These are commonly used obfuscation technique in visual media. We introduce the concepts partial privacy and strict privacy. We designed a model in privacy settings that leverages situational context and is underpinned by our human study findings. Our contributions include we propose a novel data set with geodiverse people in the wild. We performed eye tracking based human studies to explore human attributes. We propose a model that is inspired by our human study. We are the first to investigate the impact of face obfuscation scenarios on automated human attributes prediction. About our data set, we propose the diversity in people and context data set, DPAC. It is unique in various ways. It consists of images of people in diverse and realistic settings. It is the first dataset of its kind to address the geodiversity problem. It is rich with extensive human annotations. It comes with both the face and body bounding boxes and includes automated annotations as well. Moving on to the psychophysics studies. Based on previous literature, we hypothesize that humans have an ability to recognize human attributes with considerable reliability under the absence of facial information. We investigate this hypothesis with the help of our human study with eye tracking. We first took images from our DPAC dataset and created 4 versions of each image: cropped obfuscated, in which a target is cropped and face obfuscated; all obfuscated, where all the faces are obfuscated; target obfuscated, where only a target's face is obfuscated; no obfuscation, where none of the faces are obfuscated. And this is the setup. While the participants took the experiments, we recorded their eye movements with the help of an eye tracking device. Answering the question, what situational cues are exploited in privacy conditions for human attributes prediction? We make 3 observations with supporting eye tracking data, and our results are statistically significant. The first observation states the role of situational context in age and gender prediction. For age estimation, our empirical findings show that participants did rely on the situational context for age estimation of a target by further estimating the age of the teammates or by inferring the relationship. For gender estimation, we noticed that in some scenarios where participants might have reasoned out from the situational context when bodily cues were misleading, confusing, or insufficient. These scenarios include a woman wearing a military uniform, or even the gender of children, which can be hard to predict. The second observation states that for emotion prediction, the objects and background information, like whether it is a tourist spot or a protest is going on, this information can be helpful. The third observation shows for emotion prediction, the people at the proximity of a target with certain interactions receive a relatively higher intensity of fixation than unrelated people or those far away from a target. Overall, our human study findings are encouraging since they suggest the potential to mimic such human behavior in machines for better explainability. With this line of thought, our proposed model, context-guided human attributes prediction network, is guided by our human findings. The target and situational context branches are designed to capture our empirical findings, and the features from the 2 branches are fused to predict the attributes from image data. And since our model is designed in privacy settings, therefore, unlike the other models, we didn't explicitly encode the facial information. First, the target branch. It is designed to capture the post-guided features of a crop target, which helps in disentangling information from a target person and occluded regions. For this, first, 18 post landmarks are generated that come with XY coordinates and a confidence score. These landmarks are utilized to generate 18 Gaussian heat maps centered on XY coordinates. Heat maps are set to 0 for landmarks with a low confidence score. This prevents feature extraction from occluded regions of a target. Global features using ResNet 34 as the backbone are element-wise multiplied with the heat maps, and then all feature vectors are max pooled to fuse information from different visible target parts. Now, these post-guided features help in emulating ISA cards with the landmarks and in capturing local features from different regions of a target. The situation context branch consists of three streams. Each stream echoes the idea from the human study observations that background information like events, scenes, and objects support human attributes interpretability. To capture event-related features like whether it is a beach party or a street protest, we use the pre-trained model on Places 365 dataset, which can help in effectively capturing event-related features. Object stream captures the objects including people from the background. In our human study, we learned that our targets, social dynamics with people, and other interactions with the environment gave a better understanding of the attributes. For capturing this information, we leverage graph attention network. First, an image is split into patches of size 30 by 30. Each patch is embedded as a vector and then represented as the nodes of a graph, and it includes an additional node of embedded features from a crop target. The nodes representing a target and the different regions of an image helps in capturing visual relationships with nearby people and objects. The attention mechanism of graph attention network helps in learning and allocating weights to the nodes of the graph. The three streams are fused to extract situational context features. Moving on to the experiments and insights into privacy-preserving human attributes analytics, we curated 3 datasets with face labels and having context. Our model is primarily designed for the privacy setting. We first tested out its performance with intact faces, that is no face obfuscation, on benchmark datasets. The reported results show that on the KRS dataset, CHAPNet outperforms all the comparison models by a large margin. It is also competitive on the emotic dataset. For the images of group dataset, unlike ours, which is trained on a whole image, the comparison models take cropped and aligned faces as input. And due to the huge difference in training samples distribution, we do not report their results here. The privacy settings include target obfuscated, where only a target's face is obfuscated in all the images, all obfuscation or strict privacy, where all the faces in the entire data are obfuscated. Now, this is an ideal setting where accidental people like the bystanders in an image are de-identified and a training dataset can reach maximum privacy protection. Partial obfuscation or partial privacy, where only a fraction of images are face obfuscated. The unobfuscated fraction of images can be of consented users, donors, or public figures, and so on. We exhaustively applied each of the 4 face obfuscation scenarios under target obfuscated and all obfuscated conditions on DPAC and benchmark datasets. Summarizing the results of the table, as one might expect, there is a monotonic decrease in performance with the increase in face obfuscation. A dataset's distribution and attributes categories have an impact on the results. The model performs far better than the chance level under the best privacy scenario, that is head obfuscation. And this is remarkable, given the human attributes prediction significantly rely on facial features. There is minimal impact when all the faces are obfuscated. It suggests that CHAPNet is effectively able to capture information from the situation context. Under the strict privacy setting, the model suppresses facial features. As the visualization shows, the model discards features from the eye, lower face, and the entire head region. However, the highlighted regions suggest that model picks features from the visible bodily cues like accessories, clothing, hair, skin, and so on. This aligns with the behavior we observed in the human study, where participants relied on bodily cues. Similar to the previous behavior we observed, that is, with the increase in face of a skated region, the model starts relying on the bodily cues. Similarly, with an increase in face of a skated images, the model starts suppressing the facial features and weights on bodily cues. With 25% partial privacy, that is, 25% of the images are face obfuscated, the model can achieve intact face level performance with less than a 2% accuracy drop. Our human findings show that age and emotion prediction significantly get impacted by the loss of facial information, suggesting some attributes might not be suitable for strict privacy. We propose the use of partial privacy over the strict privacy since it can give a boost in the performance. Summarizing our work advances existing research which relies mainly on facial information, and we show the feasibility of visual analytics under de-identification for privacy. The packed data set can benefit the researchers to study human behaviors and interactions. Humans indeed use contextual cues for determining facial attributes related to emotion, gender, and age. CHAPNet is inspired by human studies which can do privacy-aware facial attributes analytics reasonably well. Now, this is a crucial and exciting area since more and more images and videos with humans are being created and shared, and privacy is a growing concern, both for users and for regulatory agencies. Thank you for your attention. Here is the link to our project page with a code and dataset.